Hey everyone, this is Lucas, and today I am going to talk about my WWDC 2018 project. And if you don't know what WWDC is, it's Apple's Worldwide Developers Conference, so that's an acronym. And if you are a student, you can apply to get a scholarship, and that's what I did this year. I've missed out the last years. Sadly, I've been missing out on it, and I should have not done it. I've this year decided to do it, however. Let's not look back at the past. And I think I did something quite interesting. It has something to do with physics, so everything that's around us. And it's a topic that I had recently in physics class at school. And I thought it was really interesting. It was the LC circuit, or also known as electromagnetic resonant circuit, or just resonant circuit. That's what I did. That's my topic. And I'm going to show you my playground, what it's capable of, and what it is meant to display, and how I've done it. So if you're interested in that, you can find out today, and I hope you are interested in it, and feel free to continue watching. If not, this video is not for you. Let's get going. Alright, so here we are in my playground repository, and here's some information on it. As you can see, the playgrounds are written down here as well. And then some information that I haven't finished it completely. I've worked around the part that I couldn't finish and still implemented, or at least my project also contained that not finished part, which I'll show you right now because it's in the first page. It's on the first page actually, which is a little unfortunate, but yeah. So if you download it or clone it with this link or right here, download as zip, what you'll get is this, and simply open it up in Xcode. It will look like this. I just downloaded it so you have the very same experience. So if you go to Playground, this is what you'll get. And you'll see here are all the imports, and then here you have some code where you have a capacitor, a coil, and a circuit. I hope you know what these terms mean. You probably do, since that's high school knowledge, I think. At least it is here in Germany. So, right. Here's some information. I've written quite a lot, and as you can see, there's also uncommented code, so that's where your tasks are coming in. Let's read through it. The code above initializes our circuit. We supply 230 volts in the standard of Germany as voltage U, as well as ampere as current I. So you see here are dots. That means it could have been anything really, since it's a result. I just went with a number that seemed real. And implement a capacitor with 10 Henry as capacity C and a 5 centimeter long coil length L with 1,000 windings. Windings have, well, the number N, or upper capitalized N, depends on the context. I went with lowercase n. That takes in 25 square centimeters surface A. What follows now is the measuring of the capacitor's voltage and current. Since I couldn't manage to finish the app in time, I've also added an alternative variant that embeds the playground's functionality. Feel free to play around with the functionality of the app that's there. The alternative variant follows after the following code. So that's where the part is that didn't finish. So if I click play and open up the right side, you'll see a little animation, or actually not animation, a little app that I've coded, or not. It should display. It's probably running. I've had a lot of difficulties actually coding in the playground. Sometimes it just didn't update it, or I had to restart my whole computer. It was a very frustrating process actually. Okay, it's not wanting to do it. Let's just skip it for now. Alright, so then we'll just get to the part that you would have done anyway when that didn't work out. So here is where so up here I have a circuit, the coil and the capacitor and coil are right here. Implement it into the circuit, and that's what we supply it with voltage and current. Okay, down here you see that's where the live view that would have been displayed on the right. Oh, now here it is. Here you see a graph, and I couldn't manage in time to display that correctly on screen, I coded that Hall plotter myself. You see, it's not the prettiest. I just tried and worked something around. I tried and do it with Bezier path, but that didn't work out, so I just did it with views and calculated how much space has to be between all these points and how big the points can actually be, and that's why it looks a little weird. But it gets the job done. You can kind of assume that that's going to be a wave function. In this case, it would be a cosine. All right. So, and you can also edit values. So here you can see, you can go to the capacitor or coil, or just go to the voltage right there. You can update it if you'd like. But you can't really see any update anyway, so that's useless. I just incorporated it to show that I've spent time on something. I don't know if that helps anything or makes it better, but I mean, I was just kind of busy with school, and I don't want to use it as an excuse. That's why I'm trying to work around. I just wanted to show that I did work on something at least, and had the plan to get it finished, but I just couldn't manage in time, which was unfortunate. But no excuses there. It's no help. Alright, so let's get to the other part. Here, tasks, uncomment. The following block of code, click on show result for the line that displays the capacitor and display it as a graph. Now start executing the playground, see the graph shape over time. Okay, so that's what we're going to do. Here you see some variables, and they tell you what they do, what time frame should be captured. So 5 seconds. The time in seconds, so each time, space between record. That should probably be plural. Oops. So 0.1 seconds. And current time is 0. So you start at time at time 0, and then 0.0, and then you're just going to up to 5 seconds, and you measure each 0.1 seconds. All right. So let's uncomment this, and here you see some code needs indefinite execution that we need for the timer that we have here, and then here you see that it invalidates, so the timer just stops at a point where it arrives this value, so 5 seconds, and then here you see get capacitor voltage. You can also do that for the current if you wanted to. So if we click play and show it, here we can see it show over. Here we can see it. That's what it looks like. We have this little W. It's a cosine function, and that makes sense since the tension just gets less. But we'll get to that later. All right. So then here it says, okay, that's not formatting for whatever reason. Wasn't that formatted just now? Let's see. Yeah, it should be. It's not doing it. Show rendered markup. The values for this graph are taken in 5 seconds, each value recorded after a tenth of a second has passed. So that is what I explained to you. This can also be done for capacitor's current, and the function has to be changed for that. The resulting graph should be a cosine for the voltage and a sine for the current. So we've just seen a cosine, so let's see if that's for the current. It would be a sine. It should be. So let's see if that's true. We only have to change the function here. And it is indeed a sine, as you can see. Okay, decent. So that's true. And a sine for the current. Sorry about that. The following two graphs should look about the same as the ones you have measured. Note if the graphs do not show, they have to be turned on. So they're not showing, so we have to turn them on. Here's the one for the voltage, and here's the one for the current, as the functions tell us. And that's what we got too. So that's right. So we just confirmed. And now here's a question. The question is why these graphs look the way they do. Worth noting is that we presuppose that we are in an ideal optimal environment where no energy is converted due to friction. So that means that's not real, but usually in school that's what you learn until university, where you just work with optimal environments to understand the concepts. Because all you do really when you look at the real environment is take into consideration what could change those graphs. If there's friction, for instance, that graph would just, the distance between the amplitudes would just be minimized and then sometimes just get to 0. Or, well, yeah, the difference will get to 0. So then, hence do these graphs keep on reaching the same minima and maxima. So that's what I just told you, just in other words. In a real world, the amplitudes would come closer together until they are aligned. That's true as well. Let's understand why these graphs look as they do, starting with understanding the left circuit. So if you click it, you get here. And yeah, I know there are some physics or mathematical looking function, but don't be scared if you don't like physics. This isn't too hard to understand, since math is only a tool you need for physics to be put in other words, and those words are mathematical equations. Since there are two circuits, the left side is of great importance. For quick readers, see the summary at the bottom. As just seen, the left side consists of a sole power supply for the voltage and our capacitor. Since the capacitor has a capacity which is defined by electric charge Q divided by voltage, in other words charge per voltage, it can be charged until it's full. We'll use that to our advantage now. The right circuit will use the capacitor as a power supply and also a kind of free charger. Now it may slowly seem plausible why the graph for the capacitor's voltage and current were wave functions, cosine and sine, power supply and charge back. Seems like a cycle. Okay, I just thought of that I should have put a picture. To be honest, I had a project in here on the introduction page above that graph what was actually a visualization of the circuit, and I removed it. I should have probably added a picture, but I explained it here, so I hope that is good enough to help you imagine this. Because for people who do not know physics, that might be a little hard, I just thought of. Oops. Well, never mind. There's a formula for changing the capacitor with a voltage. We will not use it since Swift does not offer the needed precision natively. It looks like this. So here you see the voltage of the capacitor is the entry voltage times 1 minus e to the power of t divided by resistance times capacity. Or in code, here's where Darwin came into play, so that's a very minor use of that library, or technology as Apple calls it, which is just tension times, well, what I just explained to you in mathematical, in code. Here I just wrote the exponent as a sole constant because, well, it just looks cleaner this way. And here's elementary charge. If you want to see all the code that's here, so just go and get or actually, sorry, no. We're talking about this file. Here's my plotter. And here's some type aliases, and here are some functions. Yeah, exactly. So, to the right side of this playground, you can now see an animation of how the capacitor is charged. Note how electrons move from negative pole minus to the positive pole. Since we look at electrons, this is visualized in the electric current direction. So that's important. That's an important term to know if you don't know it. So usually it would move from plus to minus, but if we look out of the perspective of the electrons, they move from minus to plus. So at least when we move in the positive area of those wave functions. So here, tap to start animation, that's what we do, and that's what you get. You see the electrons, here you see the plus pole and the minus pole, and they move. So that's exactly what we figured out. And here you see the charging process. Here you see how much it actually is charged currently. And here you see the maximum capacity. That's the capacity that our capacitor actually has, and that's the current value. So you see, it can be charged to a certain value, so that will be 5.0, and it can't get charged beyond that, but the electrons would still move. So we're full. And you see, they still move, but we're full, and it's not charging more, since that's the maximum that's possible. Exactly, so we're done with this part. So, and here's a summary of the left circuit. So here I wrote that down. If someone's a fast reader, since that should just be for 3 minutes, but that's not enough time. I don't know if that's okay to do, but in my opinion, it was just a very educational topic, and I wanted to do it so badly that I just decided to give shortcut if you only really have 3 minutes. All we need the left circuit for is to charge the capacitor, since the capacitor will serve as our power supply in the right circuit. And that's why I think that it's not that bad that we do not have a visualization. We have the code, which sort of represents it, and all the left circuit is for is actually just charge the capacitor. We could have just simply used the right part and presuppose that we have a charged capacitor. So that's alright in my opinion. Okay, so then here we have the same code again. I should have probably done that globally, but I thought it would just make more sense if we now create it again so we can look at it and do not need an image. And here's some explanation. There's no visualization of any app as in the other two pages, So here we have setup. We have a charged capacitor that acts as a power supply. So you see, as mentioned in the playground page for the left circuit, and a coil. This setup with the charged capacitor is of great importance for our wave functions. Let's see what happens by having a look at the graph of the capacitor's current once more. Please turn it on if it doesn't show. So here we go. That's what it looks like. See again our little sign. So, to 1/4 period, flowing current to the other plate. If you don't know what a capacitor is, there is a plate capacitor, which we are talking about here. I've never really seen any other kind of capacitor in a resonant circuit, so I thought that would be something we just presuppose as basic knowledge. Exactly. So, since our charged capacitor acts as a power supply, which I told you, electrons now move in the conductor toward the coil. This current we call discharge current. Once they reach it, so the coil, a magnetic field is building up due to a rule of physics. This is something that's very basic. If there are electrons, so basically if there's current flowing in a conductor, there's just a magnetic field around it. With a coil, it's much stronger due to its windings. Remember that one of the plates of the capacitor is charged, the other not, leading to that tension that causes the discharge current. That's simply the idea of how current flows. What comes into play now is the self-inductance. The rule is when a magnetic field changes, a conductor, here the coil, self-inducts, which means current flows. So that's different current. This current flows in the opposite direction of the current that caused it, which is reasoned by the rule of Lenz. So that's a rule. So if we have self-inductance and we have a new current as a result, the self-inducted current, it flows in the opposite direction. That's not the only way of using the rule of Lenz though. We'll come to that later. If you click on it, you can always read up on it. This isn't too important for our function since all it does is slow down the growth of the current. So it is sort of important because that's why it is the wave function. If you turn it on, it would pretty much immediately be on the maximum value. So it would be very rough. So it's sort of important, but not actually. But to have a nice graph like this, it's important. Sorry. Since the self-inductant current flows in the opposite direction, you can imagine these electrons collide with the electrons of the current caused by the capacitor. All right. So that's to 1/4 period. So, one whole period would be up here, I think. Up here. So that would be a whole period. So 1/4 would be, well, here it's half. So that's here, right? So up to here, all that does right now is just smoothing it out. So 1/4 to 1/2, so basically from here to here. At some point, the electrons reach the other plate of the capacitor and the discharge current falls. Makes sense, because if all electrons are on the other side, there is no tension between both plates. Well, there is a new tension, but not the same tension, so the discharge current just falls. But that falling of the current leads, once again, to a change of the magnetic field. Since the electrons started to flow, that is what led to the magnetic field and to the self-inductance. Now it stops flowing, which is also a change in the magnetic field, and now you know, which then leads to self-inductance one more time. This self-inductance also works with the rule of Lenz, but this time not in the opposite way. But now it wants to preserve the magnetic field. That's what I told you earlier. There's another way of using that rule. To preserve the magnetic field. Hence does that inductive current flow the same direction as our previous discharge current. So that means earlier, what we got here, that's when we reached the other side. And here would fall, right? So if we didn't have that self-inductance, that would be a very rough curve. And now here would just fall. That would again be a very rough curve. But that self-inductance of the second way to understand the rule of Lenz is what leads to that smoothing out. The new self-inducted current that wants to preserve that magnetic field just charges it still, but it smoothens out. It's not immediately. It just goes slowly and reaches zero. And that's why the graph looks like this. So thanks to the rule of Lenz and to self-inductance, that's why it is smooth as it is right here. And that's why a nice sine or cosine results. All right. Where did we left off? This self-inductance also works with the rule of Lenz, but now wants to preserve the magnetic field, hence does the inductive current flow the same direction as our previous discharge current. The inductance current therefore is the reason that the current doesn't fall back to zero all of a sudden, but instead slowly decrease until it's zero. So basically what I explained to you just in summary, so it's shorter. The second half of a period, so one whole period, since we could just move around where we want it to be. So we are here right now, right? That's where we were from 1/4 from here to 1/2, so here. Now the capacitor is charged the opposite way, and all of this starts over, but also in the opposite direction, since which can be seen in this sine curve. So if you remember, all electrons were at one place once, and then they moved right here, and then they were just smoothed out by the self-inductance. And now we are on the other side, so we flow in the opposite direction. So all of that repeats just in the opposite direction. That's why it looks like this. So all of this you can use again just in the other direction. And that just keeps on going in an optimal, not influence environment where there's no friction or anything like that. And that's it. That's my playground. And I think that really explained it well. I think I wanted an explanation like this when I had it in school. And yeah, I hope using code that this has been very helpful. And I think with all the nice graphs that the playground offer, it did exactly that. So if you have any questions, let me know. And as a finishing comment, let's say it like that, I have to say I'm not very confident. I've seen other people do more programmatically more interesting concepts. And let's say I do not completely regret picking this topic because I think I like this idea. I don't necessarily know if that is what Apple wants to see, but it has been my first project, so I see it as an option to learn how to work this and to use pressure, because I have been in fear of not being able to finish. I submitted that 3 minutes and I never had my heart beat that fast, I think, in my whole lifetime. So that was very interesting. Obviously I'd be sad if I didn't make it, but other people have done very interesting things, I have to admit. And next year I have final exams, so I don't know if I'll be able to get there. So I just hope that this is something Apple thinks is interesting. I certainly think it is interesting. I don't know if it has been enough code. All I did was really code and a little animation with SpriteKit. That was something I learned new. I didn't know how to do that, which you can see here. That is all the code for that animation. Where you spawn electrons and get the scene. It's a little function to just display it in a nicer way. And here's all its setup, which is pretty interesting. And then here you get the graph controller. You see, that's not too much code. That's just 186 lines, and even formatted with a lot of spacing in between. Here, that's just like 164. Then we have that file here, which is like the plotter and those few functions that you only have to translate to code, basically. So that's not much thinking. I think the most thinking part was this, and the part that really had me learn something was the animation stuff right there. iOS apps I know how to work, and I didn't even finish, so that's embarrassing. Yeah, so not too much code. I bet other people have done way more than this, but there has certainly been a learning curve. There has been pressure that I had to work with, which was a very good experience. I had to write essays and try and make them interesting and think about how I want to approach everything, come up with an idea to solve problems like the clutter. And I think I did that well. I just didn't display it well in the app. So if you do that on its own, it actually looks pretty cool. I could have used it, but I wanted to use the playground's capabilities too, so that's what I've shown. I've never worked with Darwin, I've never worked with Sprite Kit. So again, there has been a learning curve. I've talked to other people if I didn't know how to solve something, where to go and read up or something like that. I asked my friend where to read about Sprite Kit, so I've also kind of learned how to use my networking to get to a place where I learn for myself, so that was certainly useful. And I tell you all of this because I just want to share that experience with you pre-WWDC, because I think the event itself and the keynote isn't all that is there to it. I think that's all, this whole experience with programming, all of that, is very key to. So yeah, that's it. I'm also going to add all of this to the WWDC 2018 repository. I'm actually on it. I haven't uploaded a video yet. If you scroll down here, that's me. So that will be where my YouTube video is going to be. Exactly, so check out the playground if you're interested in code. I think I coded it in a way that it's understandable. And I hope you like this. I hope it has been educational, because that was the main point with this. I wanted to show that I can educate people with code that I write. And in physics, programming code is very essential nowadays, because not all tools that teachers use are good. And if you know how to use code, I think that is something very useful for especially people in physics, researchers, or even teachers. So that's it. And it's not even that difficult, I don't think. I mean, writing a plotter maybe, but using the playground to display your functions in a loop, I think that isn't too difficult. And it's very interesting. It's a very interesting use and productive use of code that doesn't only involve thinking about how to write software. Okay, cool. So thanks for watching. I hope you enjoyed it. And let me know in the comments below what you think of this. If you have any feedback, if you think that this was a good idea or not for WWDC, if you think that that's something Apple would see, that's controversial probably, but let me know. I really love to hear any opinion if there's anyone who finishes this whole video. And that's it. Thanks for watching again, and see you later.